Question 8 then. Which of these is going to convert pressure variations in sound waves into alternating currents? What's going to turn sound into electricity? Well, amplifier does kind of the reverse. It uses electricity to produce sound. Same with headphones, same with loudspeakers. They're all using electricity to make sound. A microphone takes in sound and converts it into electricity, so it's going to be D, a microphone. We have this magnet for the next part going into the coil. It's going to generate some sort of deflection on the meter. So this is measuring currents in ammeter here. And we've got to work out what we can do to make the direction of this current reverse. So essentially what we've got to do is reverse the change that's producing this current in the first place. So let's have a look at this option. Move the North Pole to the left more rapidly. If we do that, it's the same sort of change, it's just bigger. So what we're going to get is a bigger current, but it's still going to go the same direction. So the needle is still going to go towards the right in this case. Keep the magnet still and move the coil to the left. Well, if we do that, it's kind of the opposite of what we started with, because here we've got our magnet going into the coil. If I move the coil away, then the coil and the magnet are being separated rather than coming together. It's the opposite change, so it's going to have to be B. Just check the other two to make sure that they're definitely wrong. Keep the magnet still and move the coil to the right. Well, that's basically the same as moving the magnet to the left, isn't it? Both of those are going to mean that you've got your magnet and you've got your coil and they're coming in. Whether it's doing that or whether it's doing that does not matter. There's a relative motion there that's going to cause the needle to go to the right. Move the North Pole into the left and then suddenly stop it. That again, we've still got a North Pole going in that way, so the coil and the magnet are coming together, and we haven't sort of reversed the direction of the magnet or anything, so we're still going to get the same direction of current for all of those, other than B. Moving on, we have the magnet dropped through 3 coils. This is a really nice question. This one makes the voltage with GCSE generated nice and clear. So the magnet is falling and it's getting faster and faster. It's accelerating due to gravity. We can see that from this graph. The question is how. We need to state and explain. So we need to say 2 ways in which it changes, and we need to explain why we can see that it's changing, particularly that it's accelerating. So just looking at these 3 different patterns, we've got this, we've got this, we've got this, we can see 2 big changes. We can see that the pattern is getting more squashed together and it's getting more tall as we go as well. Why is that? Well, when this magnet drops in slowly through coil A, we've got a slow change which takes a longer time, so that's why it's spread out here. By the time it reaches coil C, it's going very quickly, so the effect is over a much shorter time period, so that's why the whole thing is scrunched up here. Secondly, because it's falling slowly through here, the change isn't very big, so we're not going to generate much voltage. But if we look at coil C, when it's going much faster, then the magnet moving faster is going to result in a bigger voltage. So you were looking at a 4 marker here. We're looking at state and explain for 2 different things. You can say the peaks get higher, 1 mark, because we've got a greater rate of change in the magnetic field, 2nd mark. The width of the peaks get less, 1 mark, because the faster the magnet means that we've got a shorter time for the magnet to travel through the coil, 2nd mark. So that's 4 in total. Why does the meter in figure 11, why can we not use that to obtain the data for the graph in figure 12? We need to have a look at both of these now, don't we? There we go. So why is it that we can't use this meter to give us this graph? That's the question. Let's move those in. Alright. So many pieces of paper. So this is an analog meter. You can see it's got a little needle that sort of goes backwards and forwards. I'm dropping this magnet through 3 coils. It's going to produce a little voltage in a very short amount of time. I mean, this axis here goes up to 500 milliseconds. That's half a second. Now, if you can read that dial, that meter, and figure out what the voltage is every sort of 10 milliseconds or whatever and write it down in that time over the course of half a second, you're a better man than I am. Or indeed lady. So the idea is the time involved in this is very, very short. There's your first mark. It says 500 milliseconds on there, so you can quote that. That will give you another mark there. And you need to link either of those ideas for your first mark with an explanation. So you could say the meter isn't going to respond quickly enough, because your meter essentially, if you want to get this sort of graph, it needs to go negative, then positive, negative, then positive, negative, then positive. It's got to do that in the space of half a second. You're not going to be able to read that. And also, the meter may simply not be able to shake that quickly. So you could say the time involved is very short, or it's only 500 milliseconds for the whole thing. And then you link that with either the meter can't respond quickly enough, or a human or a person could not take or record the readings quickly enough. It's not acceptable to say, by the way, that human reaction times are insufficient, because it's not really about the time between you seeing it and you writing down the results. It's that the whole thing happens too quickly for you to get all that data. A delay is not the issue here, is what we're trying to say. We move on, we get our final question, which is this transformer. Chances are, if we've got a transformer, we're going to need to use the transformer equation, and wouldn't you just know it, in this case we are. So it says, calculate the number of turns in the secondary coil, you use an equation selected from the list of equations at the end of this paper. Well, what do we know? We know VP, we know VS, we know NP, we're trying to figure out NS. So, finding the equation shouldn't be too tricky. We know what all of the letters are that we're trying to find. And if we look there, it's going to be this one here. There's your VP, VS, NP and NS. It's a 2 marker, so it shouldn't be too complicated. We've got no unit conversions for a start, everything's in volts, or just turns for the ends. So we're going to go, let's move this map screen out. There we go. So we've got our VP over VS is equal to NP over NS, and we're trying to figure out what NS is. Now the trick to figuring out something that's at the bottom of your fractions here, if you've got one fraction equal to another fraction, you're trying to get at this thing here, just flip them. That'll make things a lot easier. So we have VS over VP must equal NS over NP. There it is, and to rearrange to get NS, all we need to do is multiply both sides by NP. So you would write that out properly, of course. I'm going to cheat because I have a board marker. So it's NP times VS over VP. Show the numbers in. So NP, number of turns in the primary. I mean, you don't even have to interpret for this question because it just tells you NP is 100. Might as well just get that down. 100 times, we've got VS over VP, which is 60, over VP 240. And if you show that in the calculator, that will give you 25. So we'll end up with NS 25 turns. You won't need units for that because it's a number, just a number of turns there. You've got 1 mark for using the equation and 1 mark for rearranging the equation and evaluating it to get the 25. And that is question 8.